a satellite and the deployment of solar panel. Let me start with the challenge we are facing on, and how industry and research center try to solve this kind of challenges. We are talking about this kind of problem. We have a chassis, which is the body of the satellite orbiting in the space. And during its operating life, we need to consider the possibility to deploy and fold the solar panel. And this activity, this movement is driven by simple actuation mechanism and must be performed in the way that the satellite is not deviated, is not disturbing too much, in order to avoid a loss of a trajectory or a change of attitude, etc. This kind of design is performed using the following approach. We have to consider the problem. We have to make things simple, because we are the mechanism is in the space. If the mechanism is too complex, there is a high risk of failure, and the satellite has to work in a very severe environment, and we have to maintain a satellite cheaper as possible. We have to avoid too much high level of weight for cost, etc., etc. So, which is the typical approach? Let me start with one example. So we have to maintain a minimal weight, because every kilogram of satellite is you have to pay to put in the orbit through a launcher, so we have to reduce the weight. But we have also the need to maintain high level of structural integrity, in order to avoid vibration or failure due to vibration or crack or too high level of stress, etc. The deployment system is typically kinematic. There is no electronic or other mechanisms which are too complex or can have a failure in the space. And you have to consider the control must be prepared a priori. You cannot control every single second of the satellite life, so you have to maintain the satellite autonomous as possible. Which is the idea? You have the spring, the solar panel folded. They are close to the chassis, and through a torsion spring you can start the kinematic movement of the panel. You have to let the panel deploying, but at some point you have to block the deployment to have the panel horizontally displaced. And this system again is simple, slow and low weight, but the energy must be enough to ensure the deployment, and we have to consider the impacts. So there are a lot of problems. We can start with the chassis, solar panel, joints, ideal joint. Then we can introduce a spring. We can consider the activation of the movement. We have to consider the presence of stop, but not with the complex geometry, etc. We have to model it with a simple element in order to evaluate all different conditions. So at the beginning we have a body for the chassis, bodies for the solar panel, some ideal joints, some torsion spring. Nothing more complex than this. And we have to avoid this kind of modelization at the beginning. This will be something that we will introduce when our knowledge on the satellite will be more deep. We need to be sure that our satellite works, not that we have to create a wonderful shape of the geometry. At the beginning, we need to be sure that the solar panel can be deployed. And the same other typical problem is the following. This is the typical lab in which you can test your satellite and your equipment, and these tests are very expensive. So also this test can be modeled in the virtual world. So you create the simulation equipment, you compare the simulation result with the tested results, and you can evaluate the structural problem, mechanical problem, thermal problem, acoustic problem before in the simulation environment, and then in the test lab. The typical approach in this case is to validate the model from structural point of view, mechanical point of view, etc., in order to reduce the number of tests. So we have the combination of multi-body world and the structural world. So we have a flexible multi-body system. At the end of our design, we will create a solar panel with the flexible bodies, and we will introduce an advanced modelization of it. The last example is about Thales Alenia Space, so Italian-French company, very close to your university. And in this case, we want to show that the multi-body analysis is very, very important in this kind of application. Every component in the satellite is submitted to severe environment condition during launch and during life. Human intervention is excluded to repair or modify. So every component must be tested on ground carefully, and on ground is impossible to represent all these conditions. So we need the usage of simulation. And we can test with simple model, we can test with advanced model, we can test in ideal condition, we can test with disturbances. So year after year, multi-body simulation became more and more important to help the design, to increase the reliability of the model, and to provide any kind of input and to validate the model. For example, there is the possibility to simulate two-panel solar array in a not synchronized way. So if you have a problem in the synchronization, the system doesn't work in the right way, and you can have some problem in the asset of the satellite. You have to consider this. So we need to simulate this phenomena. Considering the vibration, we have to introduce flexibility. We have to run parametric analysis, modifying structural data, inertial data, spring data, friction data, and orbital velocity, etc., etc., etc. So we have at the end thousands of simulation in order to find the best parameter to validate your design and to match your requirements. This is a typical approach in this industry. So let me start with you for creating the model. If there are questions, please stop me. And so let's start with new Adams view session. We create a new model. We provide a name to the model, for example, Satellite 2022, in order to have a unique name. We have no gravity in our model. Our model is defined with units like millimeter, kilogram, Newton, second, degrees, modified system, international system of units. And please select a working directory in which you want to save model and results. After this, click on OK button and the interface is ready for our modelization. As I told you yesterday, we will use a lot icons, buttons here, model browser, some icons here. We will use or will not, we will use only some features under menus, and I show you or I teach you some basic capabilities of the code. Again, I am not in presence today, so I cannot see. If you have problem, please stop me, write to the professor, and ask me to repeat a step or some part of the modelization. Don't be shy, because it's important that everybody of us are aligned with the model. The first thing we create is the chassis of our model. The chassis in the first design will be fixed to the ground, so we cannot model at the beginning the satellite orbiting in the space. It is an approximation, yes, but we want to focus our attention on the deployment of the solar panel. And for the level we are in the modelization, this is enough. So to create a chassis, we can select a body and the geometry like a box. So this is the geometry to select. When you click on this icon, the container showing the box geometry is opened, and you see we want to create a new part with this geometrical representation. We want to define precisely the length, the height, and the depth of our body. So we flag this field and we introduce 1000 for length, 1800 for height, and 1500 for depth. And we move the mouse on the screen and we select and click in correspondence of the center of the universe, the center of the plane, the 0, 0, 0 position. When you click, you see that your body is created on the screen. You can rotate the screen and you see the body. This body is made with steel, so the mass and inertia is probably too much, because in the real satellite we have no a full body like this, but it is only a chassis containing electronic equipment, other mechanisms, etc., etc. But at this moment we don't need this level of detail. We only focus our attention that we have a body. This body must be relocated in the space. We want to have the center of mass exactly in the 0, 0 position. We have many methods to do it: relocating the body, relocating the geometry, relocating the center of mass with coordinates, clicking and dragging the geometry, etc., etc. So we can use one of these options to make to show you one of the easiest way. Please go with the mouse in correspondence of this icon, in which you see a arrow and a box. You see that some of this icon has a small black arrow in the bottom. When you you have this capability, click the right button of the mouse and you can open other features. And you can see that we have different methods like repositioning by clicking and dragging, repositioning by inserting data, repositioning using parametric data. If you click in this icon, 2 boxes and 1 arrow, this box means that you can translate an object, clicking the initial position and clicking the end position. So click this icon, click the body you want to move. From which point? From this point, initial position, the center of mass, to this point, which is the center of the universe. And you relocate the chassis in the space. This part is called by Adams part 2. We don't like this name because when we talk about a satellite, this part is called the chassis. So we can rename this part. There is a specific option for renaming object. If you move here, rename. Now you see that every name is defined by the name of the model, followed by the name of the body. So we can change in this way, chassis, and the body is renamed. This body has 6 degrees of freedoms at the moment. There is no any constraint. So Adams writes for you 6 differential equations. And if we simulate this body, if we have forces applied to the body can fly in the 3D space. But we want to make this body fixed to the universe. So under connectors, we have library of joints. Among these joints, we find fixed joint. A fixed joint introduces 6 algebraic equations, removing all degree of freedom of a body. So if you click the fixed joint, here you have a container asking you for a fixed joint, the selection of 2 bodies, the selection of a position of the body, and eventually the definition of the orientation of the joint. So move on the screen, selecting chassis and click, then selecting round and click, and then selecting the center of mass of the chassis and click. You create in this way the joint. And before to go ahead, I need to explain you an important thing. When we create a joint or when we create a force, a multi-body code, like Adams, always asks you which is the first body to connect and which is the second body to connect. The joint will be created between 2 bodies and is not important for the joint creation, which is the first body and which is the second body. But the sequence, the order of choice is important when you ask information from the joint. If I want to know the reaction force on the fixed joint, I will get a value when the reaction force is belonging to the chassis part, and we have the same reaction forces but with a different sign if we ask the reaction forces belonging to the ground. So when we ask measure, it is important to know the order of selection. And the same will be taken into account when we create revolute joint or spherical joint or translational joint. In case of revolute and translational joint, the order is also important, because when or if we apply a actuation, it will be the first body that moves with respect to the second body. So it is important to remember this. If you make a mistake, you can simply switch the body, so you can invert the order of selection. Remember this and pay attention on the topology also in this case. Also, this name is not good, because joint 1 has no any sense, has any meaning for me. If I have a model with 100 bodies, joint 1, joint 100 is difficult to check. So please rename it also. And this could be called, for example, X chassis round. So you can invent a name which helps you to understand the topology of the model. Okay, so this is the first joint. So our model contains now 2 bodies, chassis and ground, 1 connection, no motion, no forces. I suggest you, in order to avoid any problem, to save sometimes and regularly your session and your model. To save a session, a working session, go to File and Save Database. You save a binary file with the name of the model in your working directory. If you close Adams View and in 10 years from now you open Adams View, you can load your session and you restore exactly the model in the position you created, you save it. So we can save our activity. Instead, if you go to File, Export, you can save an Adams View command file, which is the model only, no analysis, no results, no customization. It's only the model in ASCII format, so readable, editable file. Again, in the working directory. Command format and extension is CMD command file. So I suggest you to save both files in your directory. You will find that the binary file is more or less 10 megabytes, 20 megabytes, 100 megabytes, 1 gigabyte, because it is the history of your session, contains everything. The model is very small because it contains, the command file contains only the model. This is a binary file, so you cannot edit, you cannot read it. Instead, the command file is an ASCII file, and you can read it and modify it if you know the language. If you don't stop me, I go ahead. So, next step will be the creation of a link. A link is an element able to make the mechanism to be deployed. So you actuate the link, and the link will push the solar panel. This link must be created with some geometry and must be connected.
Can I ask a question quickly?
Yeah.
The command file is readable with which software?
With any kind of editor you want, WordPad, Notepad.
It's just a text file.
It's a text file, exactly. So we can go to bodies, and we decide we need to locate the origin of the geometry of the body we want to create. To define an origin of a geometry, we can use specific construction element like parametric point or like markers, which are points and which are reference system, location and orientation. In this model, we will use markers. So click on bodies, move on construction, and click on geometry marker. The marker belongs to ground or to any part you have already created. A body can contain thousands, millions of markers, depending on your purposes. In this case, the marker I want to create will belong to the part. Which part? Chassis. And the orientation of the marker is global XY plane. It's good for me. So how to locate the marker? There are many ways. You can simply click a point in the space and then you can modify, or you can explicitly select a position in the space. So let me show the first method. Click the chassis, because this is the part to which you want to create a marker, and then click a point in the space where you want. This is the marker we have created. This marker has a name. I don't like this name, so I rename it and I create it with the name yoke or link or leva or my part. Select a name which is good for you. This marker will be relocated. In which way? Go to the marker and click on modify option. In this panel, you find global coordinates of the marker. And in this panel, you can also find that you can locate something in a relative reference system. So it will be very useful to locate something in a mobile reference frame, in a local reference frame, not in global reference frame, because it is more easy to position a point at a specific distance along an axis of another marker instead of in global coordinates. And the same for the orientation. We will see it later. Instead of this coordinate, so remove the location and insert the following coordinates: 550 for x, 100 for y, 0 for z, and click on OK. And if you rotate, you see here the marker. You can tell me, but the marker is not in the geometry. Who cares? The geometry is only for visualization purposes. For sure, this is not the real geometry of our body. So the important thing is the mass and inertia of this body. So this marker can be located where I want in the space. In the real model, probably here I have some arc, some geometrical element containing the marker, but I don't want to spend time for this. Later, if you want, I can show that we can import any CAD model creating any kind of geometry. So the next part, the next step is creating a new bodies. And to create this body in an easy way, I want to locate it exactly in the window and to orient it with no any effort. So, which is the best way to do it? moving the working grid, this axis, in this position. So instead of inserting location and orientation data, I simply click the center of the axis and my body will be oriented easily. To change the settings of the working grid, you can go to Settings, Working Grid. The working grid can be changed in size, in spacing between dots, in color, but I want to select a new location, picking the new marker. Okay, so this is the working grid now. I repeat, settings, working grid, set location, pick, and click the new marker we have created 1 minute ago. Now, under bodies, I can select the link geometry. We create a new body with this geometry, and as before, we flag length, width, and depth of the link. Length is 700, width is 100, depth is 40. Where is the origin of the geometry? In correspondence of the marker. Which is the orientation of the body? Exactly along the vertical axis of the working grid. And this part is a new body, part 3. I rename it, and the name will be yoke. You can appreciate that we have bodies, geometry, references, local reference system, that is markers, and joint, no motion and no forces at the moment. The center of mass of the chassis and the center of mass of the link is automatically evaluated and positioned and oriented by Adams, considering that this body are defined with mass, with steel material. Okay? For example, the yoke has 24.25 kilogram of mass and inertia evaluated along X local, Y local, Z local axis. This body is not completed. We need to add another geometry to this body. Again, we can have one body, and under a body we can define all the geometries we want.
I'm sorry, I have an error. So I created the yoke, like you said, and I have an error saying invalid operand in expression.
Can you show your screen?
Of course. So I created yoke, but it keeps generating this error.
Okay, please go to File,
File,
Export, Save. Okay, okay.
okay.
Overwrite. So no
Yes.
backup, no backup. You don't need the backup.
No.
Overwrite. Okay. Now close Adams View.
Exit and don't save.
Exit. Yes, exit. Start again Adams view. Go to existing model. One second. We have to wait. Okay, existing model. Search the working directory. Select folder. In the file name, search for satellite model. In common, yes. Common, yes. Okay. Okay, you make a mistake with a sign or something else, and you make a problem, and in this way we delete the problem. Okay.
Okay, so we can reset it.
Okay.
Thank you.
I get the control again. Okay. Now I want to add another geometry to my model. So please go to Settings. Working grid, pick on this top marker. So this is the new position of the working grid. Now go to bodies, geometry link, but pay attention, we don't create a new part, but we add geometry to an existing part. This is an important thing to remember. The length of the geometry will be 100. The width will be 20. And depth will be 40. Adams asks you, first of all, to which body you want to add a geometry. So move on the screen till the name yoke is displayed and click. Then select the origin of the new geometry and maintain the axis of the new geometry in a horizontal direction. When you click, you see that we have two geometry belonging to one body. You have a modification of position, orientation, and value of mass and inertia of the body, because we have more mass now. We have another solid element here. And in fact, now the mass is not more 24.25, but 24.97 kilograms. If you have another bodies or in a different color, you create a new body. So please delete it and repeat the process, adding geometry to an existing body. So this is only one body with two geometry. Okay, so what is the connection between the link and the chassis? The link has to move in the plane, in the XY plane, global plane, allowing the link to move far from the chassis. The rotation is the only degree of freedom we allow, so we have to use a revolute joint to remove 5 degrees of freedoms. 5 degrees of freedom. So go to connector, go to revolute joint here. As before, 2 bodies, 1 location. Which is the orientation of the joint? Normal to the view, normal to grid. So the orientation is toward us, outside of the screen. So in this case is fundamental the selection of the first body and of the second body. because we will actuate with the motion the movement of the link with respect to the chassis. So move on the model searching for yoke and click, then move on the screen searching chassis and click, and then select the marker called yoke, which is located in the origin of this geometry. Select, click, and if you look the icon show you a revolute joint with the z-axis of the joint directed outside of the screen. A joint rotate locally. A joint allows a rotation, local rotation around the local z-axis. Okay, the system will move in 3D space, but the joint will maintain local z-axis, not global, local z-axis. Now we have a model with two bodies, two moving bodies, yoke and chassis, and two joints, a fixed joint and a revolute joint. The model has 12 differential equations plus 11 algebraic equations. So at the end, the model has 1 degree of freedom. We can check the topology and the goodness of our modelization using a verification feature, which is under Tools, Model Verify. You find that here Adams writes for you which is the number of the moving parts, number and type of joints, and evaluate the total degree of freedom of the model with or without redundant constraints. A redundant constraint is a constraint which remove a degree of freedom already removed by another constraint. So you can remove this redundant constraint. If you don't remove the redundant constraint, Adams remove it for you. So Adams makes always a model which works in the right way. But it is important that you as engineer, as a designer, drive, control, be master about your model. The model is verified successfully. What we want to do with this model, we want that the link rotate in this direction. So the rotation is around z-axis, clockwise orientation. In a right-hand rule model, like this, the rotation is positive around an axis if it is counterclockwise. If you use your right hand and you see X, Y, Z, you can appreciate that the rotation around an axis is counterclockwise, the positive rotation. So to apply a movement, we can select motion, ideal movement. A motion can be applied on joints or on points. In our model, we apply an actuator on joints, in particular on revolute joint. You can click this rotational icon. In this dialog box, Adams propose you a function. I don't care about this function. I will modify it. So,
professore, scusi. Mi sente?
Yes. Sì.
Credo si sia bloccato il video.
Now you can see my model rotating. Hello?
No, non ancora, not yet. We actually see your screen frozen. There is a green band.
Yes.
Yeah.
Okay. Let me change the network. You see my screen now? Rotating the model. Hello?
We do.
Yes.
We do now.
Okay. So I want to create a motion, which is an ideal actuator. Click on motion, click on joint motion, rotational joint motion. Here you find a proposed function for our motion, but I don't care about it. The important thing to remember is to select the joint. We want to apply a motion to this joint. And in fact, you see here now a motion applied to this joint. And the positive direction is this. But if you apply a motion with this positive direction, the link enter in the chassis. And this is not the behavior we want. So we need to move the link far from the from the chassis. Okay, so go to the motion modify. You find here that we have the name of the motion, the name of the joint, later we will change it, and the function with respect time of our motion. In Adams, the time is already an existing variable, state variable, and the name is time. You don't have to invent it, you don't have to create it, already exists, and the name is time. It's not important which if you use this representation, or you write time in this way, or in this way, or in this way, no problem for this. But I don't want to use this function, so I remove this function. In this field, I can write any mathematical function I want. There is no any limitation. You can write 1 million of lines of functions, complex, in the more complex as you can think. The only important thing is that the function must be coherent, mathematically speaking, and must be written with the right syntax. So you cannot omit brackets or commas, okay? But there is no limitation in the kind of function you can create. But it is evident that this field is small to write a complex function. And you can expand if you want the dialog box, but this field is always small. So we have a function builder. Click in this button. In the function builder, in this dialog box, we can write long as you want and long or vertically as you want a function using embedded mathematical function, using state variable, using numerical data, using constant and variables, using subroutine. So again, you have the full capability for writing any kind of function you want, combining all of these functions, or you can invent your function. We want to use an existing function called step. The step function allows you to move from one condition, initial condition, to another condition, final condition, using a continuous, smooth intermediate function, avoiding discontinuity, which is not real. The discontinuity doesn't exist in the standard physics. Okay, so you don't have discontinuity in your function, which is the description of the step. If you go to this icon, the question mark, you have access in Adams. You don't have to navigate in internet. You can be out of network, no problem for this. The manual is installed with the code. The manual contains more or less 30,000 pages of documentation. So you can spend 1 year of your life reading all the statement and all the instruction. So it is very, very big manual. And if you click on Adams Help, you can open the master help and basic solver, which is the most important manual. In the solver manual, you can find convention, you can find command file, modeling process, data set, statement, understanding Adams solver. So you can find the basics of multi-body dynamics and the basics of Adams, and you can find any kind of help, for example, functions, and under functions you find step. If you look the manual, you see the format of the function, the argument of the function, an extended definition, and here it is evident the step function, initial value, final value, polynomial connecting the two ends, and this is a third order function which allows the continuity of the function and of the first derivative of the function. So instead of writing this function, you can use this format. So here is the format. I can write my data in this space, but I don't want to do problem with syntax. I don't want to forget a bracket, a comma, or something else. So I can click on assist. And now in this dialog box, I have only to fill the fields with that. So the independent, yes.
Excuse me. I found impose motion but not join motion.
Is it possible? Is it possible? If you can, it's impossible. If you have a regular joint, you can click here and click the joint.
So click the joint and modify.
Yes, modify the motion, not the joint. Hello?
Hello. So I'm clicking on the joint, and all I can see is modify joint and impose.
No, modify motion. Not modify joint. Motion, join motion, click the joint, and then modify the motion.
But I still see impose motions as opposed to join motion. Okay, I'm going. Can I share my?
You don't. You okay? You probably you follow this. You go here and you impose motion here. No, please.
Yeah.
Don't use this method. So go to motion here. Click on joint motion here. Click the joint, and then modify the motion, not the joint.
Okay.
Okay. If you have another motion here, please delete it. So in the function builder, search for mathematical function, search for step, click on assist. In the independent variable, write time, which is your independent variable. The time, the initial time x0 will be 0. The ending time x1 will be 5. So we suppose that our motion is defined in 5 seconds. The initial value of the movement will be 0, but it is a rotation, so an angular value. So please switch to angular and now click 0. And the final value will be 90 degrees, but the motion is in clockwise direction, so minus 90 degrees, because it is in the opposite direction. When you click on OK, the syntax is written in the right way, and when you have an angular data, you see this letter D means degrees. So this number is interpreted in degrees. Otherwise, it is considered in radians. So it is important for angular value in degrees to have this suffix D. If you plot the preview of your function, this is the preview from 0 to minus 90 degrees. Then you can click on OK. The function is introduced in the motion dialog box. Then click on OK. And now we have a model with 2 bodies, 1 fixed joint, 1 revolute joint, and 1 motion. It is a kinematic model with tools, model verify, with 0 degrees of freedom. Perfect kinematic model. Okay, if we go to simulation, only for debugging purposes, we run a simulation. So we can run all the simulation we want during our design. You can go to click this icon, which is the interactive simulation. The end time of our analysis is 5 seconds. The number of steps of the output, so the number of the point we will have in our plots, diagrams, report, and animation will be 500. It is a good rule to sample the simulation with 100 steps for every second of simulation. It is a suggestion. So 5 seconds, 500 steps. If you click on play, you will see this behavior. And you must have this behavior on your model. If you have a different behavior, you made a mistake, some mistake, and you have to check. Wrong joint, wrong motion, wrong body, wrong location. You have to check which is the problem. If you want to review the analysis, please don't click again on play. You don't need to repeat the simulation. The simulation is saved, and you can review the animation, clicking on animation here or clicking on animation here. and you can see animation all the time you want without repeating the analysis. And you can visualize the icons during the animation. You can superimpose the frame during the animation, evaluating the volume occupied by the link during the animation. You can also trace the trajectory of some point during the marker, etc. So you can do many things in your model, in your post-processor. This is a basic post-processor. The advanced post-processor is activated by clicking this button, but we will see later when we will monitor the model together. Okay, we will look the results together. Please file, save database, file, export to save the model in this partial creation in order to save everything. If you have saved it before the model, Adams asks you if you want to overwrite it or if you want to have a backup. In this partial creation, we don't need the backup, so we can click on no. Any questions? Is it clear? Okay. What I want to change, the name of the joint and the name of the motion. So joint, rename, revolute between yoke and chassis, motion, rename, motion of the yoke. So there is no risk of we can understand any component we have created. Yoke, chassis, revolute joint, fixed joint, motion. It's easy to find. Focus now, enlarge your model and look the marker here at the end of the second small link. This marker. This marker is important because will be the marker to locate the internal solar panel. So it is good to rename also this marker to avoid any problem. So go to this marker, rename it, and we can call it marker end. Unique name of this marker. Now we can create the inner panel, the internal solar panel. The first thing to do, as usual, we can click settings, working grid, and pick the working grid in correspondence of this marker. Now, go to bodies, go to box, new part, the length of the box will be 20, the height of the box will be 1600, the depth of the box will be 1300. And the origin of the geometry will be exactly in correspondence of the end marker of the link. Okay, this is the solar panel. It is evident that the solar panel is not created in the right position. We need to position it correctly. But instead of position it in the global reference frame, we position it using this marker, so in a local reference frame. So we position an object relative to another reference frame. Only Adams gives you this possibility to locate object globally or locally. So please relocate what? When you create a box like this, the box is defined starting from a corner marker. We have here a corner marker belonging to the internal solar panel. We can rename the part. We can call it inner panel. So we modify this marker, but not relative to the ground, so not relative to the origin of the word here, but relatively to this marker. And we can do it not in one shot, but we can use the apply button to find the right position iteratively. For example, regarding the X position, is X coordinates, which is the right position of the marker? We have to consider the thickness of the solar panel, half outside and half inside, because here we'll have specific shape of the geometry for defining a pin connecting the object. So from longitudinal X point of view, with respect to this marker, we can define -10, 0, 0 with respect location relative to the end. If you go with a mouse close to an object and you click the right button of the mouse, you have a group of elements included in this select window, and it is evident you cannot make any mistake. So I select this marker. And if you click on apply, you see that the solar panel is relocated horizontally. We can do the same vertically. We can move down the solar panel. The height of this panel is 1600. So -1600, 0. Click on apply, and it is located in this way. And half along Z, so -750, which is the half of the depth. Click on OK, and now is located perfectly. I decide to move it in 3 ways. No, sorry, I did an error, which is the 600 and sorry, minus 10 minus 1600 minus 650 with respect this point. So this is the choice, the selection you have to do. Minus 10 minus 1600 minus 650 with respect this marker. Okay, now it's good. This is a way, but there are possibility to locate moving, inserting data, parametrically speaking, using a precision move panel. There are many methods to locate an object and orient object in the space. I want to show only some of this possibility, but you have at least 5, 6 different methods for orient and locating object. Which is the connection between the inner panel and the yoke?
Sorry.
Yes.
Can you repeat how to fix the second marker?
Yes. Here,
Thanks.
marker, modify, minus 10, minus 1600, comma, minus 650, with respect, not the global reference frame, but the local marker and reference frame. Okay?
Yeah, thanks.
Okay. So, which is the connection between the inner panel and the yoke? Again, another revolve joint. If you click a revolve joint, two bodies, one location, normal to grid. The first body will be the inner panel. The second body will be the yoke. And the position, again, will be the marker in the end of the link. And this is the new joint. And the joint here will be renamed revolve inner yoke. So we have 3 bodies, 18 degrees of freedoms, minus 6, minus 5, minus 5, minus 1, 17 constraints. We have a model with 1 degree of freedom. We have to remove this degree of freedom applying an actuation. Again, motion, joint motion, rotational joint motion, click the joint. Now we want to rotate counterclockwise the inner panel with respect to the link. And the rotation must be 180 degrees in order to have the bodies perfectly aligned. So we can use for the motion, call it the motion inner. We can have motion, modify, remove the proposed function, click on function builder, search for step, assist, 0, 5 is the range of time, 0, 180 is the range for the rotation. And our plot will be this one. We save, okay, and we save, okay. And now, if you run another simulation only for debugging purposes, 5 seconds, 500 steps, if you click on play, you will find a perfect aligned mechanism. This is rotation. This rotation is with respect to the chassis. This rotation is respect the yoke. Okay. Again, file, save, file, export, save. The last thing to do is the external panel, the external solar panel. We can repeat the same process as before, creating a bodies, etc., etc. Or, due to the fact that the external solar panel is identical to the internal solar panel, we can go to the part inner panel and select copy. Adams creates for you another part, at the moment exactly located, oriented as the original one. The name by default is the same name followed by a different index. I rename it outer panel. I can also change the color appearance. Instead of magenta, I can select, for example, green. And how I can relocate this panel with respect to the inner panel? I can use another method. Go to the icon here, right button of the mouse, and select this icon. Display the precision move dialog box. It is another method for interactively move any objects, part, point, geometry, constraint, force, group of objects, with respect to the model or other objects, selecting numbers or clicking interactively orientation, direction and orientation. So it is very easy to relocate the part called outer panel with respect, it is very easy to locate the marker of the outer panel relative to the geometry, so the marker in the corner, outer panel marker 13 or the name you have, with respect the marker belonging to the inner panel. So we translate horizontally only this body with respect a point, and which is the entity of displacement. We want to move the panel in order to be not perfectly positioned one close to the other, but with a gap between them, a gap of 30 millimeters. So we have to move horizontally a marker of 50 millimeter along X. And you have this new position. Okay, you see, in one shot we move one body to another body. Relatively or globally, it's up to us to decide in which way we want to relocate an object. Now we have to create a joint between the outer panel and the inner panel. The joint must be a revolute joint located exactly in the middle of the gap, in the middle of the depth of the solar panel, and in the bottom of the solar panel. So click on connectors, click on revolute joint between the outer panel, click, and the inner panel, click, in correspondence of the corner marker of the outer panel. The joint will be renamed revolute outer inner. And as before, I can click on Move Precision dialog box. I want to relocate the constraint with respect to the marker here. So, which is the position along Z? 650. Which is the position along Y? 0. Which is the position with respect X? Half of the gap, which is minus 15. And it is relocated. The joint is located correctly. But you can locate it with respect to the other marker or with respect any other point you want. And you can move it in any way you want. So you can modify object by inserting numbers, clicking and dragging, using precision move, and also parametrically, but we don't see this feature. Now we have 4 bodies, number of joints and motion. At the end, we have again a model with 1 degree of freedom. We have to remove this degree of freedom using motion, using rotational motion, clicking the joint, and renaming it. And you can save the system, the body, the model, etc. Which is the motion law? Function, motion modify, function builder, step, time 0, 5, 0, minus 180 degrees, because he has to rotate clockwise direction in this way. And now, if we run the simulation, 5 seconds, 500 steps, we will appreciate perfect alignment between objects, perfect alignment between objects. Okay. From the kinematic analysis, we can evaluate displacement, velocity, acceleration, and the torque in the motion, so which will be the real motor, the real actuator to apply this movement, and the kinematic behavior will be independent from the inertial characteristics, while reaction forces and actuation torque will be dependent from the inertia characteristics. And my task, one of our tasks will be the the good definition of inertia behavior, but also to dimension to preliminary size, find the size of the engine to actuate our satellite. So what is missing in our model are the measures of our model: angle, speed, acceleration, and torque. We will focus our attention only on angular rotation, angular displacement, relative angular velocity, and torque. So we will create 9 measures on our model. Let me start to create the first, related to the joint between the yoke and the chassis. If you go on this joint, selecting the icon or searching the joint in the model browser, and if you go to measure, you can create any kind of measure related to the joint. Force, reaction forces; torque, reaction torque; relative rotation; relative displacement; relative velocity; relative angular velocity, etc. I want to know the rotation of one body to another body around the axis of the joint. This is called rotation. Click on rotation and provide a name of the joint, followed by AZ, angular around local Z axis, the axis of the joint. Characteristics will be rotation. The component will be the Z component in the local axis. And I want to know the rotation of the yoke with respect to chassis. In this way, Adams writes for you the following function. AZ, rotation of the first marker with respect to the second marker, and multiply this rotation for a coefficient to transform the radians to degrees. So in any configuration of the model in a 3D space, in any orbital position, in any rotation of the full system, Adams will evaluate the local rotation of the yoke with respect to the chassis. Local rotation. You don't need to define from yourself angular between the local axis and the global axis. Adams evaluate everything for you. So, name, characteristics, component of the yoke with respect to chassis, and click on apply. And in fact, you see minus 90 degrees, which is the motion I have applied with the right sign. The second measure on this joint is the relative angular velocity, omega z, wz. The characteristic will be the relative angular velocity, component z, of the yoke with respect chassis, but when you evaluate a displacement, velocity, acceleration, angular velocity, angular acceleration, you need to insert also another reference frame here. In particular, I select the same axis of the joint, chassis marker 10 in my model, so I select chassis marker 10 here. Let me explain you this. If you ask for a displacement or angular velocity, in this case angular velocity, if you define the angular velocity of a marker, this is the global angular velocity with respect 0, 0, 0. If you define this function, it is a difference of angular velocity projected in global axis. Adams evaluate the angular velocity of the yoke minus the angular velocity of the chassis, and this is projected in the global z-axis. But if your system is flying freely in the space, the local z-axis is not the global z-axis. Imagine that your satellite is spinning around itself. The local z-axis changes continuously. I need to evaluate the local angular velocity, not the global angular velocity. So I need to define the following, which is a local difference of angular velocity. And if you want to do from yourself this evaluation, you need to use this function. And you have to multiply this function for a matrix of cosine director. And multiply again the transpose of the cosine director matrix. Imagine that for every simulation time you evaluate 9 angles, 9 parameters, multiply them for a difference of velocity, multiply them for another matrix of 9 parameters. In 1 year, you are able to evaluate half a second of the analysis. Okay, it is a very huge effort for manual evaluation. Instead, simply inserting a reference system, Adams makes this for you. So when you evaluate the relative angular velocity, select the component, select the first body from second body, and ask in which reference frame you want to print your results, to plot your results. If you click on OK, this is the behavior. Starting at 0, change velocity, and go back to 0 because the system is stopped at the end of 5 seconds. If you animate, now you can see the animation, but also the behavior numerically of the system. Okay? You can repeat the same for the joint between the yoke, the inner panel and the yoke. Measure AZ, rotation Z component from yoke. Name, rotation Z component from yoke. Apply, and this is the second measure. WZ, relative angular velocity, Z from yoke, projected along the marker of the yoke, marker 15 in my model. And this is the second behavior. Lastly, joint measure AZ, rotation Z, outer panel from inner panel, omega Z, relative angular velocity, component Z, outer panel from inner panel, but projected along the coordinates marker 21 of the inner panel. And these measures are saved here under measures. And these measures are not only measures, but also equation. Adams, you can use this equation for controlling and monitoring the system. So when I create a measure in the preprocessor, these measures are also other equations that can be used in the model. We will see later. If you close this window, you don't delete the measure. You don't need to recreate the measure. Simply go to Design Exploration, go to Measures, click on Display, and you can ask to display the measures. And save. So now we can go to the post-processor results. Instead of animation here, go to the post-processor. In the post-processor environment, you can plot, you can report, make a report, you can animate, you can do frequency analysis, vibration analysis, many other things. We focus our attention on plotting and animation. You can see that we have created 6 measures, 3 angle and 3 relative angular velocity. If you want, you can click a measure and create a plot with title, legenda, label, separator, for analysis data, analysis name, etc., etc. Every plot can be modified by you in every element, changing font, changing numbers, changing format, changing color, style, symbol, weight, title, date, blah, blah, blah. You can customize your plot. And when you want to save the plot, you can go to File, Print, and save a plot in different format for your project, for your documentation. You can also export data numerically in different format, and you can do many, many other things. If you want to create another page, click on here, select, for example, speed, and you see here this velocity. And again, or you can create more measures, more plots in the same pages with different label and different format. Displacement, velocity. Or you can create plot only of the angle, plot for the speed, etc. You can also split a page in many pages. So you can decide to plot what you want in every subviews. Okay, so you can post-process the model in the way you want. You can also create a combination of results with sum of curves, subtraction of curves, multiplication of curves, scaling, offset, interpolation, integration, derivative, splining, filtering. There are many other possibilities. And I have no time to explain what you can find under these menus. If you want to navigate between pages, you can do in the following way or in the following way. If you don't like some pages, you can click remove pages, etc., etc. If you want to create other measures only for post-processing purposes, so you don't want to introduce equations in the model, you can go to objects, and for the last analysis you have performed, you can create measures regarding position, velocity, acceleration of the center of mass of the body, or energy. You can ask for forces, torque, rotation, velocity of every joint. And regarding motion, we can ask torque, power, and other kinematic quantities. For example, we have 3 motion. Every motion is defined by, is defined with a function of time. And the motion has to move to actuate a system with inertia. Which is the torque a motor has to apply to make this movement to the satellite, to apply this movement to the satellite? I can select the motion, I can click torque, and I need to know the torque around the z-axis of the joint, component z. Click on add curves, and you can appreciate that, for example, the yoke has a behavior more or less linear. We have a starting point, then we have this magenta dotted line showing the torque of the motion applied to the yoke element. And the torque level is 50,000 Newton millimeters, 50 Newton meter. The inner motor apply a quite linear torque till this point, and then the system behaves in an evident non-linear way. And the value is minus 400,000 Newton millimeter. For the outer part, we have this non-linear behavior, the blue line, and with this value. It it is evident that the torque are too high. And we have to investigate the reason of this. We cannot accept this high value. So we go back to the model and we search for the inertial characteristics. So the chassis is made with steel, but it is fixed to the ground. So there is no influence of the chassis to the torque of the motion. The yoke is made by steel and the mass of the torque, the link, is 25 kilograms. Could be acceptable. It is an important element, must resist to important loads. We can accept it as made by steel. But the solar panel cannot be defined with steel. The solar panel is defined by many different materials. And for sure, a solar panel cannot have a weight of 325 kilograms. So in our modelization, we made a mistake, or we don't focus our attention on the inertial characteristics because we run a kinematic analysis. But from kinematic analysis, we can evaluate important information like reaction forces and torque, actuation torque. So we have to modify the material of the steel, of the solar panel. In a more advanced model, we can have a density which is an average value considering aluminium, silicium, and carbonium, and what is the material of the solar panel. To make things easy for the moment, we approximate, but it is an approximation, the density of the inner panel and the outer panel to the aluminium. So we select aluminium, apply, and immediately we have 1/3 of the inertia as before. And the same for the outer panel. We go to simulation, we go to interactive simulation, but before to run the new analysis with different inertial characteristics, we saved the previous analysis only for comparison purposes. So click on this button and save analysis old. Now run again the analysis, save it as analysis new, go to the post-processor, new page, select the two analyses, select measures. What happens to the angle? No difference. It's a kinematic analysis. The movement is not affected by the inertia characteristics. So every value is the same from angle and velocity. But if you go to results and you select the motion, for example, the yoke, of all the analysis and compare the analysis with the steel instead of aluminium and the analysis with aluminium, torque around Z, you can appreciate that we have a big difference in the torque. Before we have 50,000 Newton millimeter, now we have 17 Newton millimeter, 1/3. And the same for the inner, you can see the difference in behavior, and the outer. So now we save our model session and our model with the solar panel modified, the kinematic model has been completed, and next time we will start from this configuration for introducing the dynamic characteristics for making this model more realistic with torsion spring, brakes, stopper, design variables, parametric analysis, etc., etc., etc. So we have completed today. If you want to repeat this process from yourself in the period we have between these lessons and the next will be in April 20. I have sent to you the tutorial. This is the exercise, so you can follow the same steps we performed together today. So you can repeat the same process. And today we have completed the model, this tutorial, till page 36. So we have completed half of the tutorial. Next time we will complete the next part of the tutorial. So I suggest you for sure to save what we did together today. But if you want, it is a suggestion, try to repeat all the steps from yourself in order to have a model ready for the dynamic part. Okay, Michele, for me it's over.
Okay, thank you, Daniele. So all the material that Daniele was showing us is already available in the Microsoft Teams platform. So all you need is there, and unless there is any additional question, we close the lessons here, and we see each other on Monday. Okay, only for the students. I profit of the occasion to give you a notification. So Monday lesson will still be held remotely unless specified otherwise. If there is any change with respect to this, I will write an email to you, okay, to notify that eventually the class will be held on class. But to the present date, if nothing is being said, everything will be held remotely, okay? So we thank again Daniele Catelani, and we see each other on Monday, and I wish you a great weekend.